So yeah, hi guys, welcome to the fourth sitting of the chapter Quadrilateral. Due to some technicality, my voice was not quite audible to you. So we are going to start with this video again. So today we are going to be having our fourth sitting in which we are going to be discussing the sums that we had left earlier. The sums, like I was saying, the sums that were left earlier, we are going to be discussing those, and I will be shifting towards that theorem in which we had what? The theorem related to your triangle. So we will be having those theorems as well, the two remaining theorems of this chapter, along with the remaining sums of the chapter quadrilateral that have been left earlier. So we are going to be completing each and everything today. Hopefully I will be able to complete those theorems and you guys will be able to understand with me. So with that being said, let us just generally recall whatever we had learnt or done in our last session. So we had, you guys remember, we had completed three sums earlier, which were from your class chapter 8.1 as well, exercise 8.1. So this was the very first sum that we had done yesterday, which was show that the diagonals of a square are equal and bisect each other at 90 degrees. So in this question, you had been given that there was a square ABCD. Let's say ABCD was a square. We had to make sure that its diagonals were equal and they were bisecting each other. So you guys already knew if ABCD had been a square, then all of its four sides had been equal, right? That was the main thing. So all four sides were equal, all four angles were equal as well. They were 90 degrees each. We had both of these things. We had to make sure that AC was perpendicular to BD and AC was bisecting BD, or you can say BD was bisecting AD. That means the diagonals were bisecting each other and they were of equal length. So that was quite easy. Firstly, we had to make sure that each of the angles was 90. So for that, we did what? We had taken these complete triangles ADB and triangle BCA, right? We had taken these two triangles in which AD was equal to BC, AB was common, and each angle that was, sorry, we had to make sure the diagonals were equal, angles were 90 as well. So AD was equal to BC, AB was common, DAB was same as CBA 90 each. So using side angle side, we could say triangles were congruent and we could have proved diagonals were equal. That was the main thing that we had proven. Then we went for what? Then we had to make sure that the diagonals were bisecting each other at right angles. That was the main thing. And firstly, we had to make sure the diagonals were equal. So I had taken the help of the case where I had told you that square is a parallelogram as well, right? Square was sharing the same properties of a parallelogram. So if I had taken these two triangles, AOD and BOC, you guys see in these two triangles, I knew AD was equal to BC. Since ABCD was a square, it was also a parallelogram. In parallelogram, opposite sides are equal and parallel. So I could say angle ADO was same as angle CBO and angle DAO was same as angle BCO, right? Alternate integral angles, and we had proved that the diagonals were being bisected. That means OA was equal to OC, OD was equal to OB. Each of the four diagonals were equal, and ultimately we had taken any two adjacent triangles. In our case, we had taken AOD and COD, and we had used side congruency criteria, and ultimately we had proven that these two angles were 90. That means diagonals were bisecting each other at 90 degrees. That was the question that was discussed in the last session. We had its converse also, that in a quadrilateral, if the diagonals were bisecting one another, then it was what? Then it was a square. They were bisecting each other at 90 degrees and they were equal. So we had assumed ABCD to be any quadrilateral. Firstly, we had made sure that all its four sides were equal. So for that, we had done whatever we had done in our earlier sum. It was exactly like that, but in this question, we had taken the bottom up approach. So we had begun with the adjacent two triangles. Then we had proven these two sides equal. Similarly, we could say these two will be equal, these two will be equal, and ultimately all four sides will be equal. So that was the main thing. Now here the thing was, usually what happens is in a square, the diagonals are equal and they bisect each other at 90 degrees. So, and you guys already remember square and rhombus somewhat are similar. Just a difference is that in rhombus, none of the angle is 90 degree, exactly 90 degree. And one more thing, diagonals bisect each other at 90 degrees. They are not equal themselves. That means diagonals are not equal. They just bisect each other. That half of one will be equal to half. Half of one and half of second. Both will be different, but they will be equal to one another. That was the thing. So in this, I could say the diagonals were equal. They had been given to me that they were equal and they were bisecting each other at 90 degrees. So my only proof would have been to prove each and every side equal, which we had already done in this case. But I had told you that don't just leave your answer once you have proven all four sides equal. Just go one step further and prove its each angle to be 90 degrees. For that, we had done whatever we did in our last sum bottom up. So firstly we took two adjacent angles, then we took two adjacent triangles, then we took two opposite triangles, then we had taken all complete triangles like your ADB and BCA. So ultimately we had taken these two and we had proven that each angle was 90, and henceforth we had said the given figure was a square. So that was the next case. Now let's move forward and see. Hello Tanish. So we had this question, ABCD was a rhombus. We had to show that AC bisected angle A as well as angle C. So it was quite easy. We had taken the help of two ways. Firstly, we could have used congruency, or we could have used the property that angles opposite to equal sides are equal. For that case, we had taken that. I had told you to consider your chapter 7 in this case. So I knew if I had taken triangle ADB, firstly, so AD was equal to AB. So we could easily say angle opposite to equal sides are equal. So ADB was equal to ABD. Similarly, if we had taken this bottom triangle, CBD was equal to CDB was equal to CBD, right? These two were equal. Then I knew rhombus is a kind of a parallelogram as well. So if rhombus was a parallelogram, then alternate interior angles have to be equal. So if that was the case, then I could easily say this angle was equal to that one, this angle was equal to this one. So pair of alternate interior angles were equal. So ultimately we could have proved that it was bisecting angle B and D. That means BD was bisecting A, B and D. Similarly, we could say AC was bisecting A and C. So these were the three questions that have been discussed. If you are unable to recall them, you can do it in two possible ways. First one is to shuffle around our YouTube playlist and find that video, or you can just log on to our website, download our application, get yourself registered. We have well structured material present there. We have recorded sessions there. We have practice questions there, test series. A lot of things are present there, so you can just get yourself registered and you can have each and everything there. So you don't have to shuffle around anything. You will be having everything right in front of you. So with that being said, let's start with the today's session and start with the sum. So this was one more question. I guess you guys already recall this. ABCD was a rectangle. So this was quite easy. I'm going to start with today's session. So in today's session, we have this very first question with us. See, this question is very important. Remember, this question is very important, but this is very easy too. This is very easy, though it is very important. So for this question, you just have to make sure you have been given what? So you have been given ABCD is a parallelogram. First of all, you have been given ABCD is a parallelogram. 2 points P and Q are taken on the diagonal BD. See, we have the diagonal BD. 2 points are P and Q on it, such that DP is equal to BQ. DP is equal to BQ. We have to show that APD is congruent to CQB. APD, this triangle, is congruent to CQB, this one. Then we have to make sure that AP is equal to CQ. That means this side is equal to that one. Then we have to make sure that AQB is congruent to CPD. AQB is congruent to CPD. That means these two have to be congruent as well. Then we have to make sure that AQ is equal to CP. So ultimately we have to prove these two equal as well. And lastly, we have to make sure that APCQ is a parallelogram. So you guys see in this question, if I tell you, in this question, each and everything is related to one another. Remember, each and everything is related. Once you have proven your first part, you will be getting the second one. Once you have proven the second part, that will be helpful for your fifth. Once you have proven your third, you will be getting your fourth. And once you are done with your second and fourth, ultimately you will be getting your fifth. So remember, it is a systematic way. You have to attempt first four parts and easily you can say your fifth part is, that means APCQ is a parallelogram. So how you're going to do it? See, in these kind of questions, when you have to prove something, you have to firstly write everything that is given to you. Then you have to write what you have to prove, and then you have to begin with your proof, right? So I know you can easily write given from here. You can write ABCD is a parallelogram. So let's just write it. ABCD is a parallelogram, right? So you guys know the properties of parallelogram suggest that opposite sides are equal and parallel. That means AD will be parallel to BC and AD will be equal to BC, right? And AB will be parallel to CD and AB will be equal to CD, right? And you guys know, if this is the case, if AD is parallel to BC and BD is the transversal, can I say angle ADP, which is this one, is equal to angle CBQ, which is this one, alternate interior, right? Then if I take these two triangles, I can say angle CDP, which is this one, is equal to angle ABQ, this one. Again, alternate interior, because you guys know AD is parallel to BC and AB is parallel to CD. So BD is acting as a transversal. The pair of alternate interior angles have to be equal. So that is the main thing to be noted here. You guys understand this? So let me just mark everything. This angle was equal to that one. This angle was equal to that one, and this side is these two sides were equal, and these two sides were equal, right? So we have to prove what? We have to prove these 5 parts. Just write them down here. And lastly, we have to start with the proof. So let's start with the proof. I'm going to erase everything because I just need the proof right here. So let's erase this and start with the proof. That is necessary, so I will be keeping that written. So proof. Starting with the first part, we need to take in triangle APD and triangle CQB. We have to take these two triangles. I know AD is equal to CB. I know angle ADP equals to angle CQB. These two were equal. And one more thing, I know DP is equal to CQ. Sorry, CB. Sorry, BQ actually, not CQ. It is BQ. So you guys see, this is given as it is the property of a parallelogram. It is proven because they are the pair of alternate interior angles. And lastly, this is what? This is given to me, right? I can say side angle side, what? Triangle APD is congruent to triangle CQB, and we have to prove what? We have to prove AP is equal to CQ. I can say second part, AP is equal to CQ, CPCT, right? So AP is equal to CQ, that is CPCT. Now let's move forward and see what else we can do here. Now for the third proof. So for the third one, we need to have what? We need to have triangles CD, and you can easily say that AQ is equal to CP. So this was your first proof, this was your second. Now you guys see, in a quadrilateral, if opposite sides are of equal length, then you can say what? Then you can easily, there is one more thing, see. In a quadrilateral, if you guys know opposite sides are of equal length, the first thing that you can say about it is that it is a parallelogram. So if you are having any confusion in this, don't worry, we have one more method for this one. We can take these two triangles. See, we can take these two triangles. I know AQ is equal to PC. I know AP is equal to CQ, and this side is common, side angle side. I can easily say this angle is equal to that one, and this angle is equal to that one. So you guys see, pair of alternate interior angles are equal, opposite sides will be parallel. So once you have proven opposite sides equal and parallel, then ultimately you can say the figure is a parallelogram. So for the last proof, you have to do what? You have to just take this triangle. So in triangle AQP and triangle CQP, you guys know AQ is equal to CP, that has been proven. AP is equal to CQ, that has been proven. And you guys know PQ is equal to QP, that is common. So side, triangle AQP is congruent to triangle CQP. And now you can easily say angle AQP equals to angle CPQ, angle APQ equals to angle CQP. Both are CPCT, and they are alternate interiors too. Therefore, you can say AQ is parallel to CP and AP is parallel to CQ. Therefore, APCQ is a parallel. So I hope you guys have understood this and you don't have any doubt on this. This was the proof of your question. This was quite easy, right? So you had to prove first 4 parts. Then with the help of 4 parts, you could say this was the parallelogram, or you can do what? You could have taken these two triangles and you could have proven that alternate interior angles were equal, then ultimately the figure will be a parallelogram. The choice is yours. You can move around with this method. Choice is totally yours. Now let's see, what do we have next? It is this one. This is again very important but very easy too. This is very easy. See, ABCD is a parallelogram in which AP and CQ are perpendiculars from vertices A and C on the diagonal BD. ABCD is a parallelogram. AP and CQ are the two perpendiculars. Now guys, see if ABCD is a parallelogram. You guys already know opposite sides will be equal and they will be parallel too. Since it is a parallelogram, opposite sides are equal and parallel. Pair of alternate interior angles will be equal. So this angle will be equal to that one, and this angle will be equal to that one. So you just have to prove what? You just have to show APB is congruent to CQD and AP is equal to CQ. Now you can write given on your own, which is quite easy to write. We are going to do what? We are going to jump with the proof. So let's start with the proof. So for this, we are going to do what? We are going to take two triangles in triangle APB and triangle CQD. Right. In these two triangles, APB is this one, CQD is this one. I know AB is equal to CD. This side is equal to that one. Angle CDQ equals to, actually we won't be writing it this side, we will be writing on the other. So angle AVP equals to angle CDQ, and lastly I can say what? I can say angle APB equals to angle CQD. Now guys, see, this is given, this is proven, and this is 90 each. So guys, see, angle side, using angle side, triangle APB will be congruent to triangle CQD, and ultimately you can say what? You can say AP is equal to CQ, right? So this is the easiest proof that you can go for. This question is quite easy. So I hope you guys have understood this and you don't have any doubt in this. This is very easy. So the question that we are about to do next, it is quite typical. So I will be hoping you guys to pay more attention to that one. So with that being said, let us start with the next sum. It is this one. See, this is very important. Remember, we have to do 6 parts in this. This question is very important. Don't worry. It seems very important, but this is quite easy to do. So how we are going to do it? See, let's firstly read the statement. So what we have been given? We have been given that in triangle ABC and DEF, we have these two triangles ABC and DEF. We have these two triangles in which AB is equal to DE. AB is equal to DE. AB is parallel to DE also. AB is parallel to DE. BC is equal to EF. BC is equal to EF, and BC is parallel to EF also. We have joined ABC to the vertices DEF, and ultimately we have this kind of a figure. We have to do what? We have to prove ABED. Which portion? Let me just use the highlighter here. ABED, that means this part, this figure, this one, this one. This quadrilateral is a parallelogram. We have to prove this one as a parallelogram. Then we have to show BEFC, which is this portion right here, this one, BEFC, this one. We have to show this one as a parallelogram as well. This one has to be a parallelogram. And then we have to show that AD is parallel to CF and AD is equal to CF. That means this side is equal to that one and this side is parallel to that, right? Then ultimately we have to show ACFD, which is this one. Let me just highlight it here. So it will be this one, ACFD or ADFC, meaning is same. So ultimately that is also a parallelogram. And lastly we have to do what? We have to show AC is equal to DF. That means this side will be equal to that one, and triangle ABC is congruent to DEF. Now see, there are various things that might confuse you here, that how we are going to attempt this question. Although this is quite easy, you don't have to think much about this. You just have to do what? You just have to go for part by part. Prove your first part, you will be getting the condition for your second one. Prove your second part, you will be getting the condition for your third one. Prove your third part, you will ultimately be getting your fourth one. Once you have proven your fourth part as well, then you will be getting 3 conditions. You will be getting a figure which is a parallelogram. So a quadrilateral can be called a parallelogram as long as it has been given that a one pair of opposite sides is equal and parallel. So starting with the first proof in quadrilateral ABED. I know AB is equal to DE, AB is parallel to DE. So I can see one pair of opposite sides equal and parallel. So I can easily say ABED is a parallelogram, right? So if, before we get to the point, in a quadrilateral, if one pair of opposite sides is equal and parallel, that figure is a parallelogram. That figure is a parallelogram. That is the main proof you have to understand. So for this, for the first part, I can easily see AB is parallel to DE and AB is equal to DE. Therefore, one pair of opposite sides is equal and parallel. This implies AB DE is a parallelogram, right? AB ED, sorry, not DE, AB ED. We have to go it fully. D is totally different. AB ED is a parallelogram. Now you guys see, once you have proven AB ED is a parallelogram, then what can you say about the remaining pair of sides? Obviously, if one pair of opposite sides is equal and parallel, then another will be equal and parallel. Why? Because the given figure is a parallelogram that has been given to me. So that means if this is the case, therefore I can easily say AD will be parallel to BE and AD will be equal to BE. Right? Mark this one as your first. So you guys see, I know for the second part, I know BC is parallel to EF and BC is equal to EF, right? So you guys see, BC is parallel to EF and BC is equal to EF. That means this implies BCFE is also a parallelogram, right? Because one pair of opposite sides is equal and parallel. This is also a parallelogram, right? Then I can easily say that BE will also be parallel to CF and BE will also be equal to C, right? Now here I want to point out something that you had learned in your chapter 6, where I had told you that when you have been given 3 or more than 3 pair of lines, out of those, one is parallel to second, second is parallel to third, and third is parallel to fourth, given if that is fourth. Or let's say if we have been given 3 parallel lines. Let's say if that was the case, we had 3 parallel lines with us. Let's say this was L, this was M, and that was N. I knew L was parallel to M was parallel to N. So what we could say about L and N? So if L was parallel to M and M was parallel to N, this implied L will be parallel to N, or you can say all 3 lines were parallel. So that was the case. Now here you guys see AD is parallel to BE and AD is equal to BE. BE is parallel to CF and BE is equal to CF. So ultimately, if that is the case, if this is the case, if AD is parallel to BE and BE is parallel to CF, then ultimately I can say AD will be parallel to EF also, right? So if this is my second one, so from 1 and 2, I can easily say AD will be parallel to EF and AD will be equal to, sorry, not EF, actually CF. AD will be parallel to CF and AD will be equal to CF, right? So again, one pair of opposite sides is equal and parallel. This implies ADCF is a parallelogram. Therefore, I can easily say AC is equal to DF and AC is parallel to DF, right? Now you guys see AC is equal to DF, done. ACFD parallelogram, done. AD parallel CF, AD equals CF, done. BEFC parallelogram, done. ABED is a parallelogram, done. So we have just completed our first 5 proofs. Now we have to go for 6th one. Now for this, I just want to tell you, this can be done on your own. You can easily do it. So for this, if I just point it out, see, we have these 2 triangles, right? ABC and DEF. Now in this case, you guys see AB is equal to DE, BC is equal to EF, and AC is equal to DF. Reason being, this has been proven, this has been given, that has been given. So if I take triangles ABC and triangle DEF, I can easily say AB is equal to DE, BC is equal to EF, and AC is equal to DF. So side, 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 triangle ABC is congruent to triangle DEF, and that is what you had to prove. So I hope you don't have any doubt in this, because this was, I know we had to prove 6 parts. This question was quite lengthy, but this was not typical. This was quite easy to solve. So I hope you guys have understood this and you don't have any doubt in this. So let's just start with the remaining part of this chapter or this exercise. Let's start with the next one. So now we have what? Actually, that was the last question, I guess. So this was the very last question for your exercise 8.1. So I hope you have no doubts in your exercise 8.1, because now we are going to start with the midpoint theorem. So see, midpoint theorem. Remember, this theorem will be what? It will be dealing with your triangles. So it will be showing you that in a given triangle, if you have midpoints of the 2 sides or 3 sides, if you join all those, what you will be having. This will be coming quite handy while you're attempting your chapter 9, which is area related to your parallelograms and triangles. So that will be quite handy. So midpoint theorem, you must understand this now. You won't be having any trouble in later on your chapter 9. So what is this theorem? So I'm going to do what? I'm going to explain the theorem and I'm going to prove it. So we are going to have the proof of that one, and we are going to understand this. So this theorem is actually divided into 2 parts. The main is this, the next you are going to study, that will be the converse of this theorem. So it states that the line segment joining midpoints of 2 sides of a triangle is parallel to the third side and is half of it.